Hi, I'm Randall Heyman, a university mathematics academic. Welcome to my Corona Help playlists, where I help students and educators with quick turnaround videos during the coronavirus outbreak. So if you'd like me to make a video for you, just comment me or drop me an email. And if I think I can help you, I will do so. So I got an interesting email from a person, Rinai, who asked about this problem here. And as that's turned out, they've subsequently worked it out. But I just thought this was, one, it's a nice problem. I hadn't seen it before. It's actually quite a pretty problem. Not too difficult. Anyway, I thought I'd do it, but maybe what I want to do is do it maybe in two parts. The first part, I just want to go through some of the steps that you can take when you're faced with a difficult problem or a problem. How you might, some of the things that you might think about in approaching it, how I would sort of think through approaching a problem. And then maybe in the second video, we'll actually do the solution. But the first one should give you enough to hopefully to at least start, but probably to work it out actually. So, okay, so what can we think when we look at this problem? Well, the first thing that I would say is this: one, don't panic. Do something. So what often I see with students, that, I mean, I do it myself sometimes. You look at a problem and it's overwhelming, and it's just, you might think of one thing and then you're just sort of staring and you can't progress it. So one of the things that you can do is just keep moving. Keep moving, try something, do anything. Okay, now the second thing that's a good idea is to understand the terms. Sometimes people start these problems and they don't really understand the terms properly. So let's just talk about that. So this is an example of doing something. Well, the first thing, if we just go back and have a look, the first thing is this idea of prime powers. So n is so n is a prime power. Whoops, power. Actually, the rate I'm going, this might end up being 3 videos. N is a prime power if n equals p to the alpha, where p is a prime, and sorry, a, not alpha. Alpha is a positive integer. And don't feel, once again, just keep moving forward. If you're not comfortable with that, try some examples. That's always good to just play around. 8 equals 2 to the 3. 8 is a prime power. Um, 10 equals 5 times 2. 10 is not a prime power. And, you know, you might just want to think a bit more like 20. 5 times 2 squared is not a prime power. I mean, one of the factors there, 4, or divisors, is a prime power, but that doesn't matter. 20 itself is not a prime power. Okay, now the next thing is the Chinese remainder theorem, and I've got a video on that. So if you don't understand that, have a look at my video, Chinese remainder theorem made easy. It's actually, of all the, I don't know, 250 videos I've got, it's my most popular video. So I think something like over 350,000 views. So, but what does it say? I don't want to go into, if you don't know it, have a look it up. But the idea here is that if you had something like x is equivalent to 1 mod 3, equivalent x is equivalent to 2 mod 4, x is equivalent to 5 mod 17, and x is equivalent to 3 mod 7. Now there can be any number of these. I've chosen to do 4, but it doesn't matter for any number of these. Now, as long as if all the moduli are pairwise coprime, i.e. have GCD equal to 1, then we can use the Chinese remainder, and the Chinese remainder says that then there exists a solution. In fact, there's a unique solution. Well, let's not go into it too deeply. If you don't understand some of this stuff, then you should look up my video or some other source. So here, the GCD of 3 and 4 equals 1. The GCD of every pair has to equal 1. ... And I suppose the last one, if we were following this pattern, we would check is 17, 7 equals 1. So in this case, we can use the Chinese remainder theorem to get a solution. Okay, so what I suggest now is let's look back at the problem. What we want to do is prove that for any positive integer k, there exists k consecutive positive integers such that none of them are prime powers. So you might want to just, this is now rule 3, simplify at first. So how could you simplify? Well, there's 2 ways that come to my mind. One is primes rather than prime powers. Maybe, but the other way is that you could let k equal 1 or 2. So let's try k equals 1. So this is just saying, can we find one consecutive number, consecutive positive integer? So that's just a single positive integer in this case. That is not a prime power. Now the answer is obvious. Yes, we saw before that 10 is not a prime power, so 10 equals 5 by 2. Okay, so that's good, but now let's think. Use the Chinese remainder theorem. So what is it about 10? What is it about 10 that makes it not a prime power using the Chinese remainder theorem? So what is it? Have a think about that. What is it? Well, what's the answer? Well, one answer is that 10 is divisible by 2 primes, 2 and 5. So it can't be a prime power. Or if you wanted to be a bit more mathematical, you'd say 10 is not equal to p to the a for any prime p and positive integer a. Okay, so what we're saying is that 5 and 2 both divide 10, so 10 can't be a prime power. So i.e., to use the Chinese remainder theorem, we're saying that 10 is equivalent to 0 modulo 2 times 3. Okay. So we can do the case with k equals 1 and we can use the Chinese remainder theorem. What about k equals 2? So now what we're saying is we need 2 numbers next to each other that neither of them are prime powers. Now, if you want to play around with this a bit, you could try and come up with some. What's some that works? 17 and 18. There's an example. You might even try have a go at k equals 3. Can we come up with 3 that are not prime powers? Well, I suppose we could keep going. 17, 18, 19, actually 20, 21, 22, 23. So we've actually got much more larger than k. 24, 25 is no good. That's a prime power. So 1, 2, 3, 4, 5, 6, 7, 8. So k equals 8. It's not that hard to do. Okay, so let's go back to the k equals 2. Well, firstly, the 17, we say that 17, actually, sorry, that is a prime power, isn't it? Sorry, see, I've done that completely wrong. Well, that's all wrong because I've forgotten we're talking about prime powers, which include primes. So what's 2, k equals 2? And look, this is normal. You go off on these tangents that don't go anywhere. You make a mistake, you retreat, but just keep moving. So k equals 2. What are 2 numbers? So what do we want? We want 2 numbers that don't contain a prime power, which includes primes. Don't include a prime power. So what have we got? 2, 3, they're primes, 4, 5, 6, 7, 8, 9, that's a prime power. 10 isn't, 11 is a prime, 12. Okay, how about 14 and 15? Beautiful, we've got there. We've got 2, so we've sort of solved, if you like, we could prove the k equals 2 case by just exhibiting this, but we need to use the Chinese remainder theorem, so we have to go back to that definition of when something isn't a prime power, which we said was it's a divisor. It has 2 prime divisors. Okay, so what we're saying here is if we were going to just do the k equals 1 case with 14, we'd go k equals 0 is equivalent to 0 mod 2 by 7, and we could say that 15 equals 0 mod 3 by 5. And now the Chinese remainder theorem So if we're going to generalize this, we just say x. So this is actually x plus 1. Okay. So we're not actually quite ready for the Chinese remainder theorem. I've managed to put, I've put it in this form. For the Chinese remainder theorem, we just have to transfer this one. We just have to recast this one, because remember, for the Chinese remainder theorem, we have to actually be able to say, where is it? Here, all of these terms here are in terms of x. So we're pretty close to the Chinese remainder theorem, but we've just got that x equals plus 1 there. So what we'll do is we'll just sort of cross that out, and we'll write it in terms of x, or if you like, you put therefore x is equivalent to -1 mod 3 times 5. Now that's the same as saying that it's equivalent to 14 mod 3 times 5. That you might feel more comfortable with that. So here we've got terms of 1 equation and 2 equations that are exactly in the form of the Chinese remainder theorem. The GCD of 2 times 7 and 3 times 5 is equal to 1. So we can use the Chinese remainder theorem. And so this Chinese remainder says such an x exists. So in a general way, we have proven that there must be 2 consecutive numbers that are not prime powers. So that's good, that k equals 2 case. Now what we have to do is just extend it. So you can now you could either try k equals 3, or just a general. You might be ready now to just switch to a general K. All the time as we've been doing this, we're just getting more and more comfortable with, and it's feeding our brain with, to sort of come up with some ideas on how to solve this problem by just jiggling things around. So I'm going to stop there now. If you've got any questions about what I've done, let me know. Otherwise, at some point, maybe this afternoon, my time, which is 4 or 5 hours time, I might do the second video. Otherwise, I might leave it till the weekend or Monday. But anyway, that'll get you started, and I hope this maybe has given you some ideas about what to do when you're faced with a seemingly difficult mathematical problem that you need to solve.